I'm going to work through sample problem 18.13 first before I do sample problem 18.12 because I think it's easier to think about 12 after we kind of think about what it means to have a salt in solution. And so this problem asks us to predict whether the aqueous solutions of the following salts are acidic, basic, or neutral and write an equation for the reaction of any ions with water. And so this kind of relates to our fourth skill here on this sheet. And thinking about the fact that when we dissolve a salt in solution and make cations and anions, those cations and anions may behave as weak acids or bases. And again, that can contribute to a change in pH. So we're going to look at this both qualitatively, is what we'll have on this sample problem, and then quantitatively, which is sample problem 18.12, to think about what happens in solution. So we've got 3 steps to kind of think about, and we'll do those 3 steps with each of these salts. The first is to list all species in solution, asking, well, is this even a soluble salt? Does it dissociate? And then looking at the pieces that are in solution. So after you look at the pieces in solution, anything that's anionic has the potential to serve as a base. And anions and cations can serve as acids if they're contain highly acidic protons, or if they are highly charged metal ions. So again, we'll apply this to a few problems here to kind of think what's going on. Then after we kind of look at who's in solution, evaluate their acid-base potential, then we'll determine the contribution of any of these species to acid-base potential that can change pH. And again, this first problem looks at this qualitatively, just asking the simple question, are we going to have an acidic, basic, or neutral solution? And then we'll work through a subsequent problem where we actually look at this quantitatively, where we actually write an equation out, make an ice table, use Ka or Kb values to actually think about what the pH of that solution might be. Okay, so we have 3 salts here, and we're going to follow this same 3-step process to think about predicting whether these solutions are going to be acidic, basic, or neutral. All right, so the first salt that we have here is potassium perchlorate. So again, we're dissolving this salt in solution, so we need to ask what happens when we dissolve this in water. Well, one of the things that we need to remember is that all sodium salts are soluble. So what this means is that we've got potassium ions in solution and perchlorate ions in solution. Once we have these species in solution, we need to ask, do they have the potential to act in an acid or a base fashion? So again, looking at your rules here, anything that's anionic has the potential to serve as a base. Okay, so here's the guy that we need to ask about is how strong of a base is this? And it's not specifically written on your summary sheet, but one of the questions that you need to ask is who is your conjugate acid? And then we can evaluate what's going on. So if we look at the conjugate acid of this guy, HClO4, all right, this is perchloric acid. Wow, this is a very strong acid. Strong acids make weak conjugate bases, which means that this guy is a very weak base, which means there's no contribution to pH. So walking through that again, this guy is the conjugate base of a very strong acid. Being the conjugate base of a very strong acid, it has no basic potential. It does not want to be with a proton, so it's not going to grab a proton from solution, and so there's going to be no contribution to pH. Looking at metal ions, okay, and it's not specifically written on this sheet here, but there was another sheet that I gave you in class, which is kind of a summary of about 8 different slides that we went through and kind of worked through for salt solutions. Okay, if we have highly charged metal ions, which means it's not something that has a +1 charge, that can contribute to the acidity of the solution. Okay, this has a charge of +1, so this has no contribution to pH. So we have 2 ions in solution that both have no contribution to pH. And so what this means is we're going to have a solution that's neutral. So pretty straightforward for this first problem. So let's do that same treatment now with sodium benzoate. So again, sodium benzoate is NaCl C6H5COO. Put this into water. All sodium salts are soluble. So we make Na plus and then C6H5COO minus. Let's treat this one first because sodium and potassium behave very similarly. +1 charge, so we've got no contribution to pH from our cation here. So let's ask the question about our anion in solution. Again, anions in solution, right? Anions have the potential to serve as bases or acids. Okay, they're only going to serve as acids if they have acidic protons. There's no more acidic protons on this species. These hydrogens are attached to this carbon. So the only potential for this is to be an anion that serves as a base. To find out how well it's going to serve as a base, ask who's your conjugate acid. The conjugate acid of this is benzoic acid. And you might not need to remember what benzoic acid is, but you need to be able to recognize that this is a carboxylic acid. Carboxylic acids are weak acids. Weak acids have relatively strong conjugate bases. So this guy is going to have acid-base potential in solution. This problem asks us to write an equation for any reaction that we have in solution, so let's think about what that does. So if we've got C6H5COO minus in solution, if it finds a water molecule, what happens is, being a strong base, it will generate its conjugate acid. And when it generates that conjugate acid, it leaves behind hydroxide. Leaving behind hydroxide means it's going to allow that solution to be basic. That's why the salt of a weak acid in providing the conjugate base makes a solution basic. And we're going to see a quantitative treatment of that in sample problem 1812. All right, so let's finish out this problem here. We've got chromium nitrate. So we've got chromium nitrate here. All right, all nitrate salts are soluble. So we're going to make NO3 minus and Cr3 plus. Remembering, anything that's an anion has the potential to serve as a base. Make its conjugate acid and ask how strong of an acid is it. HNO3 minus, or HNO3, is a very strong acid. Strong acids make weak conjugate bases. So in this case, there's going to be no contribution to pH, at least from the nitrate portion. All right, so let's look over here at the Cr3 plus. Well, this is a situation where we have a highly charged metal. Highly charged metals have the ability to contribute to the acidity of the solution, and we write in an equation, we're going to see why. All right, so these salts like to exist as what we call hexahydrates. So the chromium likes to complex with 6 water molecules. And this is something you just need to know about how these metals behave. So chromium likes to complex with 6 water molecules. Now again, those 6 water molecules are neutral. So this is still a +3 charge. So what's going to happen here is this is going to have one of these water molecules let go of its proton. So we're going to have chromium now with 5 water molecules. One of them is going to let go of its, and I'm just going to write this as OH, one of them is going to let go of its proton generating hydroxide. Because this hydroxide has a -1 charge, the net of this is +2. Again, that proton gets given up to a water molecule and we generate H3O+. The fact that we generate H3O+ in solution means that solution is going to be acidic. Okay, let's walk through that one again because that's kind of some new chemistry that we've seen. Chromium likes to form complexes with 6 water, what we call ligands. These are water ligands. So it complexes with 6 water molecules. Again, those water molecules being neutral allows this whole complex to still have a +3 charge. What happens is one of those water molecules lets go of its proton to another water molecule in solution, generating H3O+. So one of those waters has become a hydroxide, which is why this whole complex now has a charge of 2+ rather than 3+. But because one of those water molecules got to give up its proton, it contributes to an increase in the H3O+ concentration, and this solution is going to be acidic. When we move on a little bit, and again we look at one of our last aspects here, and we think about understanding acid-base strength, okay? And we don't really have a sample problem that does this, but look back in your notes and understand why water that's complex to a metal gets to let go of its proton and contribute to acidity.